Second effect of the pressure is the pressure in fluids. We're going to start specifically with the pressure in liquids. So unlike the pressure in solids that acts in only one direction, following the direction of the force exerted on, the pressure in liquids acts in all directions. That's for the simple fact that particles that make up the fluid are not tightly packed, so they can move in all directions. And if we want to see this visually, if we take a plastic bag, okay, and we fill it with water, and then you do random holes from all on the surface of the plastic bag, you'll see how water will start to flow outside in all directions, and it doesn't only flow in one direction downward like the pressure in solid. Okay, so now we're gonna see the story of a can of beans that is being thrown in the sea, and it will explain to us how the pressure in liquids actually act. Okay, so first thing, when a can of bean was thrown to the sea, at first it was floating for a few seconds. As you can see here, we have the water particles, okay, and that's the first line defense. Water particles that are closer to the surface, they try to resist the thing that happened to them, which is the can being placed in their medium. So they try to push it backward, and this force exerted by the water particles molecules is called the upthrust. Okay, so I'm gonna highlight this. It's called the upthrust. But since the can is heavy enough, and we will see later on why it sinks, so the can has a density that would make it sink. So this is what happens next. The can falls into the water, and it will quite rudely displace all the water molecules. And now the can is fully sinked, and you can see how the water level will slightly rise above it. Okay, and this disturbs the molecules, the water molecules that were living in peace. So that here comes the second line of defense. Water molecule will now try to crush it. So they will work all together in order to crush it. Water molecules will push the can, trying to destroy it, because something weird entered their medium. And water molecules are trying to force themselves back together like they were in this picture, in this one or this one. Okay? So what happens is to this can that it seems that all the water molecules are together pushing, exerting the same force, which is represented by the arrows, and each in it is in a direction, in different direction, and all of them are trying to push on the can in order to destroy it. After a very, 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 very long period of time, the can will be actually crushed, so it will shrink, it will change the shape of the can will be changed slightly, and water molecule will succeed in returning back all together. Okay? Now, what are the factors affecting the liquid pressure? Because we just agreed that, yes, water or liquid can exert a pressure. So what are the factors affecting the liquid of the pressure? First thing is the height. Okay? If you take a bottle of water and you fill it with water, and then you do 3 holes, 1, 2, 3, you will see how the furthest where the water will flow is in the third one, in the lowest one, while the second will have a medium flowing, and the first one will be a very moderate flowing or very small effect of pressure flowing. That's because if we compare the amount of weight of water weight above each position, we will see how on the third level we can, this is just like theoretically, okay? So if I say, let's say I have 1, 2, 3, 4, 5, 6, 7, 8. So I have 8 particles, molecule on top of each other. If I take this specific water particle, okay, or water molecule, you can see how it's carrying 1, 2, 3, 4, 5, 6, 7 above it. So all of their effect or their force exerted downward will be accumulated on this molecule, and so from the third hole we will have the furthest flow. While if I take the water, this one, which is at level 2, you will see how only 1, 2, 3, 4, 5 water molecules are above it, so it will eventually, of course, have less force. It is carrying less force, so the water that will flow out of hole 2 would be less. Okay, and same thing if we take the water molecule that is at level 1, you will see how it's carrying only one particle above it, so this is why it will flow in a very small way, or like the effect is really decreased in compared to 2 and 3. So the first thing, or the first factor, is the height. As we go deeper in the medium, the pressure increases. Second factor is the density. Okay, if we take two pools that are the same size and we fill the first one with caramel and the second one with water, and I ask you to swim in each pool, in the caramel pool and the water pool, you will find some difficulty in order to move in the caramel pool, as the particles, even though both of them are considered liquid, but the particles in the caramel are pushing against your body in a very harder way than water particles are. So this proves that the pressure of the object also depends on the density of the liquid. Third one is the gravity. So it depends on where my medium is placed. Is it placed on Earth, where it's being pulled by a force of gravity of around 10 Newton per kilogram, or is my medium placed in Jupiter, where it's being pulled by even more pressure, more force, pulling it downward, which is around 25 Newton per kilogram, or it's on Saturn, which is close to the Earth. But the pressure can be measured anywhere, actually, and so the pressure would depend on where the medium is placed. And so if we join all three factors together, we will get the third relationship, which is, the second relationship, which is pressure in liquid depends on density times the gravity times the height. Okay, and as we can see, pressure and density, pressure and gravity, pressure and height are all directly proportional to each other. As the density increases, pressure increases, and as gravity increases, pressure increases, and as height increases, pressure increases. Now, the unit of the pressure won't change. It's still Newton per meter squared. Why? That's because density, which is in kilogram per meter cubed, gravity is in Newton per kilogram, and the height is in meter. So kilogram and kilogram will cancel each other. Meter and 1 out of this meter will cancel. We will remain by Newton, and divided by meter, and 3 will become 2. Okay, and so we will have the same exact unit for pressure, which would be converted to Pascal, or would be shifted to Pascal. Direct application. Okay, I'm not gonna go through them. You can pause the video and just make the direct calculation. Okay, it's by simply rearranging the formula every time. Let me take this one as an example. So as you can see, if I want the height, it's gonna be equal to P divided by, because this is the division and that's the multiplication, so it will be P divided by what? P over rho times G, and that's the formula, and then you just apply the rule and you get the answer. Now we know why bubbles get bigger as they rise to the surface. That's because as we go deeper, pressure increases, and so this one has a larger surface area than this one, as this particle is being influenced, or like it has an effect of a very larger pressure in compared to this one, which has a lower pressure acting on it. Okay, same thing for the medicine. For the patient bottle, the infusion is placed at an elevated position for the same reason. Same thing, the public water supply system reservoir is placed at an elevated position. And last thing, the dams are built with a wider base. That's because as we go deeper, pressure increases, and so the water particle actually here will have a very high effect in compared to the water as we go up. And this would, it's very important to make a thicker wall, or else at a very long period of time, water particles here would be able to crush the dam. So engineers, they build the dams with a wider, thicker wall at the bottom or at the base. Okay?